We continue with the yesterday's business, and we had our input VNIB against BPA, and we got our graphs in this form. We got this as difference in BCA. We got our output IC, BCA, with a couple of these graphs. And this was ID. This was emanating from having a transistor. Then we have this as our IE. We have this as our IC. Then we had our IE here, which constituted PD across here being our VDE, and our output here being our VDE. So we had started on our small single parameters. And we had said that from the input and output characteristics, we can write VDE and IC as functions of ID and VCE, whereby we are saying that VDE can be looked at as a function of ID and VCE. We look at this VDE can be looked at the variation of ID and the output VCE, the change in VCE, and IC in terms of the ID and VCE. So they all have we are looking at both of them being as functions of the input current, which we call the base current, because it's the base that determines the operation of our transistor, whether it is an NPN or a PNP or an NPN. The base here is the determinant. When you bias the base, when you give it a current, IB, is the one which activates our transistor, either to avoid current flowing through it or allow the current flowing through it. If you look at it closely, it's all about this middle part that makes your transistor active. Just like when those of you who have done this experiment here, of the chips, when you supply here, you have to make sure that you have VCC here and you have your grounding here. Okay? For no chip to be active. Otherwise, it won't give you anything. So you have to supply it with VCC so that whichever gets in here, whether it is a NAND, whether it is an OR, whether it's a NOT, or a NAND, or a node, you have to first activate it. Similarly, this IB here is what has to be applied on this other part which constitutes the base in order to give you an output or any other characteristics that you may wish to have. I beg to run a little bit fast. So for small changes, in the base emitter voltage and collector current in VBE and IC respectively. Then we have that the change in the base emitter voltage can be written as Kali VBA by Kali IB over the constant, over the VCE, and then we multiply by delta IB plus Kali VBA by Kali VCE, keeping IB the constant, and then multiplied by delta VCE. Whereas the change in IC will be the same as Kali IC by Kali IB over VCE multiplied by delta IB plus Kali IC by Kali VCE over IB multiplied by the change in VCE. We know from Ohm's law, or from the definition of resistance and voltage, the ratio of voltage to the current gives you the resistance. For that matter, this being that we are at the just for clarity, we got our transistor. Go to the we got our IC, we got our VCE, got our VBE, we got our IB, and we got our IE. And these are our terminals C, terminal A, terminal B for our transistor. So it means that VBE by IB here, the change in VBE, the change of current will give you the non-resistance or the input resistance of the transistor. Whereas when you consider this other part here, yes, when you consider this, it's a reciprocal of if we had said VCD over IC, which would be the same as the output resistance. But it's preferable if we call it impedance. So input impedance and output impedance, because resistance is more of passive and linear. Impedance is the same as when you say capacitive impedance in the capacitor and impedance in the inductor. So I will let a few of these ratios here in terms of the resistances. So let RBE equal to Kali VBE by Kali IB over VCE, and let's call this one input resistance
but preferably better if it is called impedance. And also let's call, if you look at this ratio here, you're having the ratio of the output current to the input current. So if you are comparing the ratio of the currents, you are looking at how it is gaining or how it is becoming small. So we talk of gain. That is a current gain. So this is a current gain, this is a resistance, this is a voltage gain, and then this is also a resistance. So we have our AR is equal to Kali VBE by Kali VCE, keeping our base current constant. And this would be the same as, since we are talking about VBE over VCE, we would have reverse voltage feedback. Reverse voltage feedback. We normally put a signal at the primary so that we get some feedback at the secondary. But if we're now looking at how the VBE over VCE, it's like if we were looking at how VCE divided by VBE, we would get gain. Okay? But now we are having its reciprocal, so we are looking at it in a reverse way. Considering this to be the output divided by the input. That's why we are calling it reverse voltage feedback. And then we shall have another parameter which is beta, since we are mathematicians. And beta will be the same as Kali IC by Kali IB over constant VCE, and this instead is equal, it's appropriate. You have the IC in the output, the IB in the input, so this will be the same as the forward current amplification factor or the forward current gain, if you wanted to take it that way. So this is forward current amplification factor. And then we have the last one, RCE, and this is the same as RCE would have been collect measure would have been the same as VCE, okay, delta VCE over delta IC, or change in Kali VCE by Kali IC. But instead, in our making of the parameters here, we have it as Kali IC by Kali VCE. So we shall have to say this is the same as 1 over this. So we have it as 1 over Kali IC by Kali VCE over the constant ID, or over a given value of ID. And we shall call this one output resistance. This is output resistance, or simply impedance. So we've got a few new terminologies: reverse voltage feedback, input resistance, forward current amplification, and output resistance. We also let We also let the change in base emitter voltage to equal to the VBE. We let the change in the collector emitter voltage equal to VCE, and we let the change in IB to equal to small IB, just for convenience of our writing stuff, and finally get our IC, changing IC to equal to IC. Then we can write our parameters such that our VBE is equal to, I'll wrap it here, the sums which were here, which was the same as Kali VBE by Kali IB over VCE, which we call our RBE, and should have been of a constant IB, and then plus AR VCE. Then we will have our IC equal to rho IB plus 1 over RCE. Whose phone is that? Whose phone is going to that sound? Huh? We are switching off. Twice. You don't look like I've not been seeing you trying to switch off. Is it really your phone or you are covering for someone? Mary tells the truth already. Is it true? When is it before? Yeah? When is his phone? Or we can have we check whether there is water. And there's nice water. Or we can write it as a matrix, and this matrix can be RBE, beta, AR, 1 over RCE, into IB, and VCE, giving us our 2 VBE and IC. We can derive other things from this, and when we derive them from this, we call them hybrid parameters. We can, just like we talk of hybrid maize or whatever, because when you get sweet potato and you put in the flavor for mango or for orange, you will have made a hybrid something. So other hybrid parameters, or sometimes which we call rotations, can be listed down as RBE, beta, AR, 1 over RCE, equivalent to HIE, HRE, HFE, and H naught. And how do we define this? the transistor parameters above that is to say RBE, AR, beta, RCE can be determined from the characteristics or the IV characteristics, and be determined graphically, from the input and output IV characteristics of the transistor. And this is how we do it. We draw the areas. HIE, HRE, HFE, HOE. Where this is input, reverse, forward, output. So I will have my IB, and then have my VBE. This is our input characteristics. Then I will have for the output, we have the VCE. And then we have the IC. These ones, we are getting up like that. So for a given value, VCE2 and VCE1, we will get a value here. VB1, so VBE1, or we can first draw them at once and get our whole value here as delta V, VBE. And this is for a given one value of IB. In other words, you get to see the Kali, the delta VBE being the same as Kali VCE, I need to check properly, was the same as Kali VBE by Kali IB, and we had over VCE. For the output ones, if we took a bunch of them, about the ones we met, our IB will be growing upwards, or we can make two to avoid any ambiguity. So I have two of them, so that I can get the change in the IB. So I have IB1, IB2, and this is our VCE. And this is a value for IC. So I have IC2, this is IC1. And I can take a given value here for a given value of VCE. Here, we do some analysis or some extraction of these parameters. Our AR would be the same as delta VBE by delta VCE. We have our delta VCE is here. Our delta VBE is here. And then we will be able to get our reverse direction or our reverse voltage feedback. RBE will be equal to 1 over the gradient, and what is this? Over the gradient at a given point. Gradient at a given point. If you took any point, and as you are having this graph here, you can take any slope at any point, depending on how you take a tangent. You can take a tangent here, you get a slope. You take a tangent here, you get a slope. So by taking the gradient and you get 1 over, you get the RBE. And we want RBE being the same as 1 over Kali IC by Kali IB. Beta would be the same as a change in IC over the change of IB. And that change here is IC2 minus IC1 over IB2 minus IB1. I'm just trying to derive the damn things I got in the line, but really we are not seeing where we're coming from. I'm not trying to get them out of the, by determining them graphically, by using the input and output IV characteristics of the transistor. Finally, our 1 over R, okay, our RCE will be the same as 1 over the gradient at a given point. So we now know where the RBE, AR, beta, yes. Pardon?
Yeah, IC here, right?
Where? Here. Yes, because we are having a value at a given value of VCE, you can your IB varies upwards, much as you have this being your IC. In your transistor, when you inject in the IC here, when you have your IC, it varies as much as how your IB is varying. The much that you can allow this IC to go through depends on the current that you are also having at the base. Because this collector current will be flowing across the base. So how much you have given the base will determine how much is getting across the base from the collector to the emitter. Okay, so we can now estimate the input resistance RBE. Estimation of input resistance are base emitter. Here, we want to find out the resistance that exists here, RB. So assume the diode equation. Assume the diode equation. I did not divulge so much into this diode equation. I'm sure you are doing it in solid state physics. So I did not bother. So assume the diode equation for the input characteristics. For the input characteristics, because these input characteristics are more or less or resemble those of the diode. So this is our input the IB, VBE, the output ones IC, PCE. Don't think I'm stupid. I always draw these things to show you that you have practice drawing them and understanding how they're doing. That's why I draw them here, I draw them there every time, to show you that you should be able to know how these things are drawn. Some of you may think I have enough time to always draw them everywhere. They are here, but then you pick them and there. And it's not that I want to waste chalk, but when you do, you remember. When you see, you forget. When you hear, you forget. That's why you need to have a rough paper. You can buy a 96-page book where you always write your notes when you are reading. If you can't read and you are dozing, just write. You write what you are seeing. Your hand will be writing in the brains. I'm teaching you how to survive that. So assume the diode for the input characteristics, and that means the IB, according to the diode equation, will be the same as I naught exponential VBE over T, where I naught is the function of temperature. The function of temperature, T, and the voltage across the collector and emitter. You will have to go to your solid state. I think it is I is equal to I naught. This is I naught. Then exponential V over T, simply. But now we are looking at this point here. We shall be able to talk of the initial current I naught, and then the VBE. The VC, of course, this current here determines how this diode behaves. The diode we use within a transistor. So that means our 1 over RBE, which was equal to the Kali IB by Kali VBE over the VCE, is the same as I naught over VT. That is the voltage at the temperature T, exponential VBE over the temperature I think this is VT, not T. It should be VBE over. Should have been V over V1 over V2 or something. You'll have to check within your diode equation. So this is over VT, and this is the same as IB over, because this whole thing here was the same as IB. This is IB over VT. In other words, VT is about 26 millivolts at room temperature. What is room temperature? How much? 24 degrees. Even this room temperature is that? Or this is not a room? Because I feel a bit hotter. So that means our RBE is equal to VT over IB because it was reciprocal. And this, or we can say that our RBE is equal to beta VT over IC, where IC is equal to beta IB. Beta is the same as the current amplification. So where I would have stopped by Tuesday is where the test will stop. Now, in order to understand a transistor, just like we tried to understand the network of resistors and capacitors, we talked of the making an equivalent circuit. And one equivalent circuit was Thevenin's circuit, now Norton's circuit. So we also need to, after having all these parameters, we also need to try to make this transistor look something affordable. Not this kind of circles, some lines, and some arrows. We need to make sure that it is represented in terms of these other resistances. This would be input resistance. We have another one which was RCE for the output impedance. And then after that, we can be able to know how the current is flowing and how the current is flowing in and flowing out. So for that matter, we talk of small signal. I'm avoiding to say signal because you want to laugh. Equivalent circuit. So one time a parent was complaining with the child. When the child was showing her, the 7th child was showing her the work. Then the boy was like, so this is a circuit, which we have learned, this is about, so she said, is it a circuit or a circuit? The boy said it is a circuit. And then the boy said, that's how our teacher pronounces it, and that's what I think it is. So that's why I was laughing. I was next to them, so I was laughing, facing this side, smiling. And the company, instead of looking at the kids' work and appreciate how they write, you are busy asking whether it's a circuit or a circuit or a circuit. Does it matter? It's a signal or signal, it doesn't matter. Or a signal. Others say signal or signal. Signal. So there's no difference. It's all about whether you know what it does. So we've talked of VBE being the same as RBE, IB plus AR, VCE, and also had IC equaling to beta IB plus VCE over RCE. So we know that from this kind of parameters, we learned that the first equation, equation 1, in order to be organized, equation 1 is a loop equation or mesh equation. We could group or mesh equation, so I should pull off this. Whereas equation 2, whereas equation 2 is another equation. So if we let, or before that, if you look at if we were to complete our circuit and say here we have a voltage VCE, a voltage VBE, and we are having a current flowing through, and then we determine the input resistance somewhere in here, and an output resistance here. We are saying that the voltage VBE here, this voltage is equal to the current flowing here, IB, see, times the input resistance that is existing here, plus the amplification times the VCE. So when you complete the whole circuit, you get the other side, you are having the AR. What was AR? But because of this diagram here, it's hard to conceptualize. It doesn't feel like how do you cross now and start talking of the VCE. Whereas the other one is all about almost the current, because you are talking of VCE over RCE is also current. You have the IB, this is just an amplification of the current. The factor better is an amplification. So it's more or less you are having an IC or an I1 equal to 4IB plus IC, some other I, because this will also give you some value of the IC. I don't know whether you get the point, but it's not easy to visualize here. So I'm going to draw something fresh that gives out these all places. Your RBE here, and then RCE here, with your IB and RBE here, well articulated. So if we let AR VCE to be a voltage source, remember how we draw the voltage sources? We draw and put this one there. The current source is drawing like that. Depends on where you want the hours to be, depends on you. And we let better IB be the current source. So these things which were confusing us, and these ones, because of these factors, we let them now be our source of the power. And the better would be how the power was made nice, and the better for the current source, how everything is working within it. They are for the voltage source. So if we do that, we can now withdraw our transistor circuit and get an equivalent circuit that makes us understand better what is going on within our transistor. So I will get the, I have my base. So from my B being the base, I have the base current IB, and then I meet the input resistance. So I have my R, D, E here. And then we've agreed that because of this equation, I must make sure that this part here is our voltage source. So I will get a voltage source around here. And then I'll have my line for ground all through. And then on the other side, on this other side of the transistor, I'll have a current source for this other equation. So I'll have a current source here. And with the current source, with the voltage source, the equivalent Thevenin's resistance is in series with the source. With the Norton's equivalent, the Rn is in parallel with the source. So we got our RCE here. And then we have our output here being our VCE. And we have our input here being our VBE. So this is our emitter. So the whole line here is the emitter. We have our beta ID. We have our voltage here, which is AR, VCE, and our collector is here. And I think we have managed comfortably to present our equation. So our IC goes in here. IB, and this is the equivalent circuit of the transistor. We can get simplified ones or practical equivalent circuit. Simplified, sometimes which we call practical equivalent circuit. Whereby we get our base, our RBE in input resistance. We cut off the voltage source, and then we remain with the current source. And then have our resistor here. This will be our output resistance RCE, our VCE, our VBE, RBE, IB, B, and our emitter. This is our beta, IB, this current source. This is our collector and this. I will diverge more on this our morning tomorrow, since you'll be more fresh and you will have tried to read through how I'm trying to bring two base signals on the board. But as you can see, all this section here is okay. You have VBE, VBE is there. I remember I changed this in VBE, we let it be so that it's easy to draw and write. Our IB is there. And also, when we reach the lines here, we get some resistance according to the ratios of the input base voltage as well as the base current. Then we call this our RBE. Then, but we have a depression region where there is a voltage. That voltage is the one which we say when we have our AR, VCE, then this is our voltage source. When we get the other side of the circuit by looking at the current which is flowing to the its amplification, and then so this is the Thevenin's equivalent here, and this is the Norton's equivalent of the whole circuit. And this was to make sure that we get these equations in the way of diagram, where VBE will be the same as IBRE, and then plus this other part here, which will be, so this is the sum of the voltages is equal to the sum of the PDs, and that's why we say this equation 1 is the same as the loop equation. Whereas this other one, where IC will be equal to IB multiplied by beta plus the R, I mean the VCE over this, because the current through here is the same as this voltage divided by this resistance. So here the current which is flowing here, I whatever, is the same as VCE over RC. See you tomorrow.